For regular videos on ancient cultures and forgotten civilizations, please subscribe. The Nineveh Planisphere, catalog number K8538, was unearthed by Henry Layard in the 1840s at Nineveh and is currently housed in the British Museum. It comes from the Library of Ashurbanipal, a collection of thousands of clay tablets and fragments dating back to the 7th century BCE and named after the last great king of the Neo-Assyrian Empire. The planisphere itself is a circular tablet featuring a flat front and a convex unmarked back. It is small enough to fit in the palm of a hand and has been repaired with matching clay where it was once broken. The front displays drawings of constellations and inscriptions, divided into 8 roughly equal radial sections. Some lines are marked with dots at their start and turning points, and triangular arrows indicate where certain lines end. Each segment includes the name of a constellation, along with additional details. Unfortunately, the tablet was damaged by fire in 612 BCE with the burning of the palace, leaving parts of its surface vitrified. This makes some inscriptions difficult to read, leading to speculative interpretations. However, the repeated appearance of cuneiform signs such as An, Mul, and Me suggests that the planisphere may have been primarily used for magical purposes. Along with diagrams from Egyptian sources, Mesopotamian cuneiform material provides some of the earliest evidence of astral theories and paradigms in visual form. One key aspect of this corpus is that the diagrams are often contemporary with, and sometimes found on, the primary texts related to Mesopotamian astral science. This allows us to see how ancient scholars were thinking in both textual and visual terms simultaneously, which is especially valuable for fields like astrology that depend heavily on conceptual models. In contrast to the usual list-based format of scholarly knowledge, these diagrams form a small yet significant body of work within cuneiform scholarship. But although clay tablets are well suited for pressing wedge-shaped signs, they aren't ideal for drawing the intricate curved lines needed for celestial diagrams. Despite this limitation, some cuneiform astronomers/astrologers did create complex clay sketches of celestial arrangements and astrological concepts. Scribes in Mesopotamia generally drew shapes in clay and paired them with descriptive text. These shapes could be either abstract mathematical figures or representations of real space, a skill taught from the earliest stages of scribal training and practiced throughout the history of cuneiform writing. Moreover, scribes wrote highly detailed, ekphrastic texts describing unique star configurations. Although the collection of astral diagrams is small, it is part of a broader tradition of combining visual elements with cuneiform text. In the entire collection of cuneiform astral diagrams, there is never a direct reference to the diagram in the text beside it. Any connection between the two is inferred, typically when a pattern in the text aligns with something depicted in the diagram, but this is not done explicitly as we might reference figures in modern texts. Interestingly, we have some texts that refer to drawings, but these references occur in texts without any illustrations. Strange, but I guess that means the drawings were on a separate tablet, or that diagrams were intended but never completed. Despite the absence of direct references, the preserved diagrams, even if they don't always directly correspond to the text written next to them, do share a relationship with existing texts. The text with the strongest connection to the diagram corpus is Mul Apin, a 2-tablet work that functioned as an astronomical handbook throughout most of the first millennium BCE. I've talked about it before. The circular diagrams that have been discovered seem to align with the content of Mul Apin, as they depict schematized versions of important stars over the solar year, similar to the star lists in the text. However, it's important to note that none of these connections are explicitly mentioned in either the diagrams or texts. The relationships are inferred based on the similarities between the material found in both. In most cases, the artifacts lack definitive dating, often missing the colophons that would include the date of copying, or a reliable archaeological context that would provide a date through stratigraphy. Diagrams began appearing on cuneiform sources as early as the late 3rd millennium BCE, but our earliest evidence for their use to describe astronomical and astrological phenomena appears around the 1st millennium BCE. The majority of these diagrams are concentrated in the Neo-Assyrian period, with additional examples from the Achaemenid and Hellenistic periods. So far, 13 diagrams have been confirmed, though this number is expected to grow as further studies are conducted. The diagrams can be divided into two groups based on their content: those describing stars and constellations, mostly from the Neo-Assyrian period, and those that explicitly mention zodiac signs from the Achaemenid and Hellenistic periods. Since the zodiac system was likely developed around 500 BCE, see my video on the origins of the zodiac for more information. This provides a rough time frame for dating diagrams that use zodiac signs. However, dating can be complicated by the overlap between zodiac signs and month names in many texts from this period. These diagrams are either circular or linear in shape, each offering specific advantages for depicting celestial patterns. Circular diagrams illustrate the continuous nature of the heavens, while linear diagrams allow for a more detailed focus on sections of the sky, such as the ecliptic. Linear diagrams also better align with the typical linear format of the accompanying text. Most astronomical/astrological diagrams preserved on cuneiform tablets are circular, often in the form of tables of data that are wrapped around a central point. One type of circular diagram found in ancient cuneiform texts is the circular astrolabe. These feature lists of stars arranged in various patterns, some of which were used for timekeeping. Two known examples, both Neo-Assyrian copies in fragmentary condition, date back to the late 8th or early 7th century BCE. One of these was created by the renowned scholar Nabu-Zukub-Kenu from Kalhu. These astrolabes provide data from star lists that detail the heliacal rising of stars across 3 celestial paths associated with the gods Anu, Enlil, and Ea for each of the 12 months. The circle is divided into 12 sections representing the months, and mirrors cosmological concepts found in the Enuma Elish creation myth, particularly in Tablet 5. These sections include information on constellations, the rising stars of each month, and lunar phases in relation to the sun. Apart from the astrolabe texts, 2 other notable circular diagrams depict stars and constellations that predate the zodiac. These are the Nineveh Planisphere and Tablet K8538, the Nineveh Planisphere. Unlike the astrolabes, these 2 diagrams do not share much similarity with each other. The Nineveh Planisphere is especially distinct as it is divided into 8 segments instead of the standard 12 divisions seen in other circular diagrams. In contrast, the Nineveh Planisphere retains the 12 radii structure, but focuses on describing the appearance of stars and constellations rather than their heliacal rising. It offers a rough portrayal of key stars beneath the corresponding textual description. The Nineveh Planisphere, K8538, stands out not only because of its 8-segment structure, but also due to its unique layout, which doesn't conform to the typical division of the heavens into 12 equal 30-degree sections. This diagram contains detailed imagery and text that must be read counterclockwise, though the orientation of the cuneiform writing is flexible. Of its 8 segments, 6 preserve incised drawings, and all contain text. These drawings have prompted extensive scholarly analysis. The fullest discussion of the artifact was done by Johannes Koch in his book, New Investigations into the Topography of the Babylonian Fixed Star Sky, written in German in 1989. Generally, his analysis and interpretation have prevailed. Koch's reasoning is that since the object was found in Nineveh, it must have been usable in Nineveh, so he concluded that it was related to Nineveh's latitude at 36 degrees. He estimated a date for its making shortly before the destruction of the palace in 612 BCE, so around 650. He produced a thorough study that aligns the diagram with known constellations from the astronomical series Mul-Apin. Koch primarily focused on the segments that could be identified with known stars and constellations, while largely overlooking the more cryptic mystical and magical inscriptions also present in the diagram. These strings of repeated syllables and phrases suggest a deeper connection to astrological or magical traditions. but further study is required to fully understand how this text relates to the Mu'apin and other celestial literature. Koch concluded that the map represented the night sky on the 3rd or 4th of January. The rectangular shape at the top is Gemini, and the stars contained in the oval shape are the Pleiades. The 2 triangles in the lower right are marking the bright stars of Pegasus. Some scholars believe that the Nineveh Planisphere may have been used to determine the time of the New Year festival in the spring, and could have been employed annually for this purpose. However, the general consensus is that the diagrams were more focused on revealing relationships between the heavenly bodies and astrological interpretations, rather than used as devices for calculation or reckoning. Diagrams are a way to convey knowledge visually. When trying to determine the relationship between objects, a diagram is inspectable. It makes things clear, whereas a text is opaque. The circular diagrams fit well within the Babylonian conception of space in the celestial sphere. Babylonian astronomy lacked a coordinate system, like our celestial longitude and latitude, and this is why we don't find grid-based star maps. None of these diagrams include numerical values, which are typically found in mathematical diagrams to clarify relationships. The preserved diagrams are full of astrological content, such as omens, rather than the mathematical complexity of Mesopotamian astronomy like zigzag or step functions. Perhaps this is why the relationship between text and diagram is often thematically interlinked but never made explicit. The diagrams played the same role as commentary texts, providing expanded interpretations of what is written. In 2008, Alan Bond, a mechanical engineer, and Mark Hempsell, an aeronautical engineer, published a Sumerian observation of the Kephal's impact event. This was not an academic paper. They bypassed the peer review process and went right to the public with a self-published book. In it, Bond and Hempsell claim that the Nineveh Planisphere, which they identified as Sumerian, records an asteroid impact that occurred on the 29th of June, 3123 BCE. According to them, this event was the basis for several ancient myths, including the biblical destruction of Sodom and Gomorrah and the Greek myth of Phaeton, who crashed the sun chariot of his father, the sun god Helios. The Kufels landslide, a massive rock slide in the Austrian Alps, was suggested as the location of this asteroid impact. While Bond and Hempsell argue that the tablet depicts the event, they admit that the specific part of the tablet recording the impact is missing. Sometimes people who specialize in other fields make attempts to interpret ancient documents and relate it to their own field. The interest is admirable, but for a study to be interdisciplinary, such people really should work together with those who specialize in cuneiform and in ancient Mesopotamian astronomy. Bond and Hempsell went into it by themselves, and so their research lacks context. The press release about their book even claimed they translated the artifact for the first time, when in fact it had been translated several times before. We do know how to read cuneiform. Why would an artifact from around 700 BCE have a record of an impact from 2,400 years earlier? They hypothesized that it was copied from an earlier work, which they think was a night notebook from a Sumerian astronomer. But why would they need to copy it? What would be the purpose? The problem is that although many Mesopotamian star names are Sumerian, and this indicates at least an interest in astronomy in the Sumerian period, there are no known astronomical texts from Sumer. Our first evidence of actual knowledge that astronomical phenomena are periodic and of the use of mathematics in application to the stars is from the Old Babylonian period, which is more than a millennium after Bond and Hempsell want to place the original star map. A major issue with their argument is the wrong chronology. Radiocarbon dating of wood buried by the landslide places the event around 9,800 years, plus or minus 100 years, before present, about 4,000 years before the date proposed by Bond and Hempsell. Furthermore, Kephal's was not formed by a single landslide event, but by several over time, which undermines the impact explanation. Even more detrimental to their proposal is the lack of evidence for an impact at the Kephal's site. What we see instead is a massive landslide formation around half a kilometer thick and 5 kilometers in diameter. In the mid-20th century, some geologists proposed an impact hypothesis to explain the glass found at the site, suggesting it might have been formed by an asteroid impact. Geologists today, however, argue that the glass was created when rocks melted during the landslide. There is no impact crater. Bond and Hempsel attribute this to the asteroid's unusually shallow angle of approach, around 6 degrees, which they argue caused the asteroid to clip the top of Gamskogel Mountain, leading to the catastrophic landslide without leaving a crater. However, this explanation is problematic. No planar deformation features, PDFs, have been found in the quartz at Kuffels, features that are typically created by high-pressure impacts. Instead, the quartz shows lamellar deformation from tectonic processes. For an asteroid impact to cause such an event, the physics would dictate that it leaves significant evidence, a large crater, an ejecta blanket, and widespread fracturing. Even a grazing impact would produce noticeable features like shocked quartz, and if the asteroid was large enough to vaporize, it would have caused extensive damage to the mountain, likely creating a crater instead of just a landslide. The researchers suggest that the asteroid, after clipping the mountain, was not a solid object, but this raises more questions than answers. If the asteroid impacted hard enough to vaporize, it nevertheless should have created a crater, fractured rocks, and shocked quartz, none of which are present. Breaking up the impactor into smaller fragments wouldn't prevent these effects. It would simply result in multiple smaller impacts, still releasing the same amount of energy. Because there is no real evidence supporting an impact event at Kuffels, and key indicators of such an event like shocked quartz with planar deformation features, PDFs, impact glass, a crater, microcraters, remains of an impactor, or abnormal levels of elements and isotopes linked to meteoroids are all absent, the idea that Kuffels was formed by an asteroid impact is no longer viewed as a plausible theory by the scientific community. Bond and Hempsel's idea has instilled greater interest in the planisphere by the general public, and other claims about it have appeared on the internet. I'm aware that 2 other men are trying to keep the impact theory alive by proposing that the clay tablet is actually referring to a comet impact in the year 2193 BCE that supposedly brought down the Akkadian Empire. This idea has gotten even less traction, despite the fact that the authors in their papers love to talk about how much smarter they are than Assyriologists. Their work has never been published. Despite the flaws in the impact theory, the Nineveh Planisphere remains an important artifact. Along with a few other diagrams, it is part of a small collection that preserves graphical depictions of astronomical and astrological ideas. The relatively small number of known diagrams shows that Mesopotamian scholars did not rely heavily on diagrams for developing or recording their astronomical and astrological concepts. While the discovery of additional diagrams is possible, it's unlikely they would represent an entirely new approach to diagramming. Instead, they would likely resemble the ones we have. Still, these diagrams reveal the creative ways Mesopotamian scribes visualized and conveyed complex celestial theories. Thank you for watching. If you like this channel and want to help keep it alive, please consider becoming a channel patron at patreon.com/worldofantiquity. Or you can give a one-time donation with a super thanks here on YouTube. You might like my little e-booklet, Why Ancient History Matters. It's designed to persuade people that the subject is important, even in the modern world. You might also wish to use it to help spread the word. So feel free to share it with someone you know. It's free for anyone who wants it. I've left a link in the description box below the video for you to grab a copy. Catch you later.